それでは時間となりましたので、セミナーを開始いたします。本日、座長を務めますのは、九州大学アジア・オセアニア研究教育機構、金シュムハ准教授です。シュムハ先生、よろしくお願いいたします。
Thank you very much for the introduction. And it is my great pleasure today to welcome you all to the 216th edition of the QAOS Brownback Seminar. And today it is my great pleasure to welcome Professor Willy Wong from the Faculty of Information Science and Electrical Engineering within the Department of Informatics. And today he will be talking about teaching machines to detect what we can't feel. I'm very excited to hear more about that. But first of all, let me tell you a bit about Professor Wong. So Professor Wong is currently, as I said, a professor within the Department of Informatics. And prior to coming to Japan, he served as a full professor at the University of Toronto, where he was for nearly 25 years. He received his bachelor's degree in physics and his master's and doctoral degrees in physics and biomedical engineering, all from the University of Toronto. Professor Wong's connection with Japan began in the late 1990s when he concluded a postdoctoral research stay through the JSPS program. Since then, he has maintained a long and productive collaborations with many Japanese researchers on topics such as auditory science and retinal implants. His current research focuses on developing algorithms for sensory impairments and advancing theoretical neuroscience. With this very impressive background, it is my great pleasure to now hand it over to Professor Wong. And just as a side note, if you do have any questions for Professor Wong after his presentation, please do not hesitate to post them in the chat, either in English or in Japanese. So without further ado, Professor Wong, the floor is yours.
Well, thank you very much for that wonderful introduction, Professor Schumacher. Can everyone hear me?
Yes.
Okay. Thank you. So just give me a second to share my slides here. Okay, wonderful. Well, it's such a pleasure to join everyone here virtually. In addition to Professor Schumacher, I just wanted to say a warm thanks to both Professor Abedin and Professor Prakash, who, and actually everyone as part of the Brown Bag Seminar as well, too, for this wonderful opportunity. Okay, so I don't need to go over this again, but I just wanted to recount an interesting story. So in addition to coming to Japan very early on in my career, I actually did 2 sabbaticals. The most recent one was in 2022 at Kyushu University. And my first sabbatical was also at Kyushu University. It was in 2007. And during that time there was nothing here. Like there's a lot of students complain that Itoshima has nothing, which I don't agree with, but there literally was nothing at that point here. There was no East Campus. The only thing that was here were the 3 buildings, West 2, 3, and 4, that comprise the Faculty of Engineering, as well as my department, which is, of course, Information Science and Electrical Engineering. There was only one cafeteria available. There was no choice. Everyone had to go to Big Dora. So anyway, it was an interesting time, and I've watched this university develop, and it's really a surprise that I'm here at this point as a professor here, joining all of you. Okay, so I'll just tell you a little bit about my laboratory. So I head up the Lab for Sensory Information Processing. We're interested in how information is processed by sensory systems, not just the mechanism, but also possible disorders and how we sort of diagnose these disorders. So typically by sensory systems, I'm interested in all of them, but we spend the most time on what really are typically considered the most important systems for us. One is the auditory system, how we hear, and the other, which is the visual system, how we see. And I'm going to, in particular, focus on how we see today. So here's a picture of some of the people affiliated with the lab. Apart from the students and some collaborators, a very important person is Haruna Fujihira, who is an assistant professor in my lab. Okay, today I'd like to talk to you about some work that we have done in solving general problems in medical diagnosis. General problems. Now, of course, we've been applying these particular algorithms to sensory systems, but actually the problems we are solving are so general and so usable, and given that there's a very general audience today, I would like to describe these problems as generally or as generically as possible. So the first problem has to do with multidimensional testing, and I think all of us have had this experience if we've ever gone to a clinic or to a hospital. Invariably, we're asked to do a bunch of tests. Now, these tests, of course, are important and they're useful, but they can be time-consuming and can possibly cause stress, particularly for younger and older people. And so one question we might ask here is there a way to cut down on the amount of time required to do all of these tests? We may not be able to cut out all the tests, but the question is, can we cut down the amount of time to do all of these tests? A second problem has to do with what I call functional and structural data. These are two words that are very, very well known and well used within the medical field. So to illustrate this, let's imagine you had to go see the doctor. You have pain, for example, in your leg. And so, of course, the doctor asks you questions. When does it hurt? Does it hurt when you sit down? Does it hurt when you stand? Can you walk up the stairs? They ask you a bunch of questions. So that's normally part of the visit to the medical clinic. But in addition to that, they also take your x-ray. And so it's kind of funny here because you've already got one sort of set of answers or data that you get from the doctor asking you questions, but there is also this entirely different aspect here where they want to take some other type of medical information. So a plausible question is, why do we need both? Okay, why isn't one of them just sufficient? Why can't we just take the x-rays? Another thing is, how do you possibly combine this information? Well, it turns out we need both these information here because they have there are sort of merits and demerits, advantages and disadvantages to both of them. So when we talk about these questions that the doctor asks us, this is really functional data. The doctor is interested in how you are able to function or not able to function in day-to-day life. In the other case, we're taking what we, in essence, is structural data. It's taking some form of objective view of what's going on inside your body, which is great, but it doesn't often tell you how a person is able to function. Okay, so we've looked at why do we need both, and also how do we combine this information. So next, what I'd like to do is to show you the work we've done in developing algorithms to solve these problems, and in particular, to apply them to glaucoma screening. Okay, so glaucoma is a vision disease that happens particularly when we get older, and I want to talk to you about that next. So what is glaucoma? So glaucoma is a leading cause of blindness in the world. It often progresses very slowly, but the problem is once you've lost vision due to glaucoma, there's no way for you to gain it back. So here's an illustration down below here. Here's a person who might be perhaps driving, and this is what they see if they have healthy vision. If they're afflicted with glaucoma, on the other hand, they might have vision that looks like this, where you get this sort of tunnel vision. You're only able to see over a very narrow field of view. So one of the difficulties is in detecting the presence of glaucoma and even monitoring its progression. Now, if you just look at these two examples here, you might say, well, this is trivial. It's very easy to see that the person is suffering over here, or maybe the person's able to self-report. It turns out it's not the case. Because we lose our vision so slowly, it's difficult for us to know how much we've lost when this progression happens at such a slow pace. So often people don't know that they're missing part of their vision until it is actually tested. So the physiological origin, I just want to spend a moment to talk about that, comes about because there's liquid inside the eye, and when there is an abnormally high pressure inside the eye, it's going to end up pressing at the back here where you have the optic nerve. And this presents a very big problem because the optic nerve is how we get our information of what we see and send it to the brain. And if we damage the optic nerve, the brain will no longer be able to see what is outside. Okay, so how do we test for or screen for glaucoma? Well, in much of the sort of the Western world, I'm talking about Europe, in North America, and certainly also in Japan, South Korea, many countries, we put the patient in front of this large machine, which does what we call a visual field test. Okay, so what happens here is that you're going to see little points of light in the visual field, and we're trying to check what is the minimum level of brightness required for you to see in a given particular location or spot. So here's one example. I'm going to show a light on the right-hand side. So the patient is asked to fixate on this plus dot, and then a light is going to come on like this. Okay, so assuming the patient is able to see this, next what we're going to do is to lower the light intensity to make it harder. So this next one illustrates that like this. Okay, and we keep adjusting it until the person's barely able to see what's going on. We call this the threshold. And we're interested in mapping the threshold all throughout the visual field. And so the next thing we're going to do is to move to a different location, and let's say we test over here, and we do this until we fill up the entire visual field. Okay, so just to go back to what I talked about before, this is an example of functional testing because it shows to us exactly what a person is able to see or not able to see. The advantage is it's very useful information, tells the doctor immediately, oh, you can see well in this part of your visual field, but maybe in this part of the visual field you cannot. The disadvantage here is that it is time costly. You're going to see in a moment here that it takes quite a lot of time to map out the entire visual field and to find the threshold at every particular location. Another thing is, if you've ever done these particular tests, is it's incredibly, incredibly noisy, which means that basically I can sit you down, get you to do the test, and then maybe give you a little bit of break, and then get you to do the test again. You might see actually quite different results. And this is a problem for clinicians because we can't have a good estimate of what the person is able to see. Okay, so let me show you an example of a visual test. So these numbers that you see on the left-hand side here represent the threshold. Okay, so this is the level of light required for a person to see. And basically on this chart here, a high value means good vision. So if you get a score of 30, it means you've got very good vision there. On the other hand, you can see certain parts like this here and here, where it goes down to 0. It means, unfortunately, that the person is having an incredibly difficult time to see what's happening. And on the right-hand side here, we translate these sets of numbers into some sort of grayscale plot, really to give us a good sort of spatial understanding of what goes on. So we can see that largely in the middle and in the lower part of the hemisphere here, the person has relatively good vision. But certainly when we go to the side, and particularly in this region here, which represents the zeros that we saw over here, the vision turns out to be very poor. Okay, so I mentioned a moment ago here the time required to do these tests. If you count up the number of locations, there's approximately 50 of them. Okay. And each one of them will require a number of trials to move the light intensity up and down. And so typically, I write down the old approach, but really it is actually the current approach used in many hospitals around the world. It takes about 5 to 7 trials at one location to find the threshold, and we're going to multiply this by about 50 locations. What you're looking at is about 300 trials, and this is only in one eye. And so typically we optimize this so that the person is able to do it within 7 to 8 minutes. That doesn't seem like a whole lot of time here, but if you take the other eye as well too, and everything associated with it, and these are often much older patients here who have difficulty with concentration, keeping with the task for a very long time here, this turns out to be quite a cognitive load on people. The only other thing I want to say here is, while we're conducting the same test many, many, many times, so from this perspective, this is an example of what I talked about before, which is multi-dimensional testing. We're doing the same test, but we're repeating it many times over. But let's come back to the key issue. The key issue here is, well, these tests are taking time, it's difficult, they're also noisy as well too. Are there ways that we can mitigate? Is there ways that we can improve this test so that it's not so much of a burden for people? So there's one way that people have come up with, okay? So this has something to do with structural correlations. So this is an example of the back of the eye, and you can see the nerve fibers that run to the optic nerve. So the optic nerve enters this little hole and goes towards the brain. But otherwise, what it's doing here is it's taking information from the visual field and communicating it along these particular paths. Now, because these particular nerve fibers are arranged in such a well-defined bundle or sort of arrangement, it allows us to predict how the pattern of vision loss will appear on the visual tests. In a simple way of putting this, it means that if a person has difficulty seeing in this part of their visual field, they'll likely have difficulty all along this particular path as well too. So there's structural correlation. Knowing one thing gives me information about another location. So it means that I don't have to test both of them quite as much. To make it even simpler, let me bring it back to our favorite topic in school, which is testing, right? So we've all been tested in school many, many times. So typically, and I was quite good at math in high school and middle school and elementary school. If we know a person is good at math, typically they're likely going to be good at physics and computer science, anything that's allied with logical thinking and mathematics. So it means, in some sense, if I already know this person's good here, I don't need to test them quite as much on those related fields. But on the other hand, being good at math, does it say necessarily that you are good at music or sports? That's not the case, right? So it doesn't tell you anything about that, but so you'll need to spend time testing those particular subject areas, but at least you save the time from having to test them on physics and other sort of areas that are related to math. Okay, so we came up with an algorithm to make use of these correlations, and we gave this particular algorithm, or I should say my student gave this algorithm a particular name. He called it, for reasons quite interestingly, he called it Toronto. Okay, so this is the algorithm called Toronto. And Toronto stands for a trial-oriented sort of testing. That's where it gets the TO. I won't explain that particular name, but it is a really interesting mathematical algorithm to make use of these structural correlations, right? That's the whole point. How do we use these correlations to cut down testing time? I think it is a very beautiful theoretical work. And as a person who is very interested in math, that interests me a lot, but perhaps today is not the best day to get into a very highly technical explanation. So instead, I decided to give you something else. I will talk to you about the inventor of Toronto. Okay, so this is a picture of Dr. Bill Shi. He was one of my, well, actually, he was my final PhD student at the University of Toronto before I moved to Kyushu University. This is a photo taken in September of this year because I went back to Toronto to visit. So let me tell you a little bit about Dr. Bill Shi. Not only did he invent this marvelous algorithm called Toronto, but he himself is really an incredible person as well, too. So he graduated from engineering science. So this is our elite program as part of engineering. Only the top students are able to get into this program. And he graduated with this undergraduate degree there. Afterwards, he wanted to do a PhD. So he did his PhD with me. And the topic of this PhD, one of the things he did was to invent the Toronto algorithm. But he didn't just do a PhD, he actually did a medical degree simultaneously to doing the PhD. Okay, this is incredible here, okay? I have difficulty doing one thing in my life. He's doing multiple things at the same time. So he will be soon, okay, a graduate of engineering program, a doctor in engineering, as in a PhD, and also soon to be a doctor in medicine as well, too. It's just absolutely brilliant. He can run circles around me, a very, very smart individual. Okay, so I won't be, unfortunately, telling you a whole lot about how the algorithm works, but let me at least show to you how Toronto does relative to basically other types of approaches out there. Remember, once again, we're trying to speed up testing. So here is the evolution of algorithms in basically visual testing. So the first time we started to use computers for visual field testing was in the 1980s, using these adaptive staircase methods. And it took, as I told you, around 300 trials to do about 50 measurements within the visual field. In the 1990s, there came a new approach, which essentially is to use Bayesian updating. So ZES, CETA, Quest. These are all variants of a particular algorithm that is very well known and still used to this day. And in fact, when you look at CETA and CETA Fast, these are two of the standard algorithms that are used in hospitals around the world in order to determine your visual field. So if you go to the hospital, very likely you're being tested using CETA. But even in these cases, we're still upwards of 200 to 300 trials per eye. Now, more recently, of course, there's advances in machine learning, and there's also advances in understanding the physiology of what's happening. So in the 2010s, there were these new algorithms using exactly what I was talking about, spatial correlation. So these methods like SVELT and SOARS also uses spatial information or spatial correlation. But you can see, so they give you a little bit of advantage, but still, we're still sort of quite close together. So let me show you next what happens with Toronto. So Toronto, which my former student Bill came up with, is a real radical advance here, which cuts down on the number of trials down to about half. So it means that an ordinary test, which could have taken 15 minutes, can now be done in just a few minutes, which reduces the burden not just on the patients, but also on the hospital flow, because a clinic here will see hundreds of patients every week. And the quicker, the more efficient you can get these patients through, the easier it is for the clinic. Okay, so I'm just going to show you a little bit about how Toronto works. I hope I'm doing okay with my time here. So on the left here, this is, let's say this is the visual field that you can get after 300 trials. So next, let's see what happens when we use Toronto to estimate these particular values. So in B here, we show Toronto running, but after testing only 10 locations. Just 10 locations, we test them once. I test once here, 2, 3, 4, 5, 6, 7, 8, 9, 10. I test each location just once, and I test 10 locations. That's all I do. So this is really just maybe 3% of the 300 typically taken to obtain a full visual field. Now, if you want to stop there, it's okay. You won't get a great an answer, but you will still get some response. And the interesting thing is, it's quite a similar match, even though we've tested only a very small subset of the values. In particular, take a look at all these locations. We never even tested them once, yet we get some particular value. Are they great estimates? No, but we've only done 3% of the testing. All right, now let's increase the number of trials to 20 and to 30. So even in this case, we're only doing 30 trials, which is only 10% of the number of usual tests required. And then once again here, there are vast parts of the visual field we haven't even looked at. There's no tests anywhere in these regions, and yet you can see these numbers converging very nicely to the true visual fields that represents the person's ability to see. Okay, so in essence here, Toronto works very fast. It is, we believe, the fastest algorithm in the world when it comes to testing vision. All right, so to conclude this here, Toronto is essentially performing n-dimensional base updating. This is in itself theoretically a really, really interesting concept of how it works. Unfortunately, I don't have time to get into it, but it solves one of the problems we hope in terms of multidimensional testing. Now, there were two problems I gave to you, right? There's this first one here, but there is a second one also about combining functional and structural data. So I can see I'm running out of time, so I'm going to hurry it up a little bit. So as it turns out, To monitor glaucoma, doctors do not rely just on visual field tests, but they also use imaging tests like OCT to examine the structural damage in the eye. So what is OCT? The OCT, you can think of it like an X-ray. It's imaging the back of the eye and then basically checking out the health of the optical nerve. Essentially, it's trying to see here if there's abnormally high pressure, you're going to lose these layers of cells here. It will become thinner. And by seeing that, they'll be able to diagnose whether the glaucoma is progressing or not. So the advantages of this, once again, this is structural data. It is objective. No matter how many times you take it, you're going to get the same result. But the disadvantage here is it doesn't actually tell you what the person is able to see. Okay, so you can see the complementary aspect of functional versus structural data. So what is our solution to this? Well, we've developed a new way to essentially do data fusion. So one of the problems here is you've got the visual field information, which is the functional data. You've got the structural data, which is the OCT. How do you combine this to come up with a better way to do medical diagnosis? Well, here is our solution for glaucoma. So we take the OCT, the structural data, we combine it together with the noisy visual thresholds, and we pass it through a deep learning neural network. Now, this by itself is very standard. There's many people working on machine learning methods, on AI, which use neural networks, so that's not a surprise. Our particular innovation is to introduce this particular loss function, which is a little bit hard to explain, okay, ordinarily, but bottom line is this. Okay, so remember here, this is objective. This is OCT, and no matter how many times you take it, you're always going to get the same number. Down here, this is very useful for us. Unfortunately, it's also very noisy. So just this by itself is great for information, but it's not very reliable information. So what does this algorithm do? This neural network essentially takes the OCT via this loss function, and it cleans up the visual threshold. So now let me show an example of actual patient data. So everything I've shown you today is actual data that we've taken from patients back in Toronto in Canada. So here's a visual field, okay? And you can see a number here, MD. This is mean deviation. On average, how bad is this person's vision? So you can see some loss here and some loss here, but overall, it's not so bad. So minus 1.5 dB means it's slightly lower than on average if we take the whole visual field. Next, they also have the OCT. And what we notice from the OCT is that there's particular thinning in this particular part of the retina. So what we can do is to say, well, this doesn't look so good, but it seems as if the person got a little bit lucky and they got a better result than they actually should be expected to have. So when we pass it through our neural network algorithm, we increase the amount of vision loss over here that we expect the person to have, and we also darken this region as well too, and we assign provisionally a slightly worse MD score. Okay, so this we use to help clean up and remove the noise inside the visual field. Okay, so I'm almost at the end here. All right, so how do we use this particular technique to help us monitor glaucoma detection? Well, this is the way we do it. So if the doctor only has access to the visual field, they can look at the mean deviation score over a several-year period. So over here, the person started to see the ophthalmologist in their 70s, and they went for a 5-year period. And you can certainly see that it is decreasing over time, which means that at some point, this person needs some intervention. They need medicine, and possibly they need surgery as well, too. But this is only apparent in 5 years. Let's say the person only came for 1 year. Remember here, we're doing this in real time. We want to find out if they're progressing and stop the progression as soon as possible. So we have 3 measurements, which comes out from the very first visit. The first time they come to the clinic, we make a measurement. That's their baseline. And then on top of that, in Canada, they have a 6-month visit and then a 1-year visit. So there are 2 more over here. So if you just look at these 3 values, you can say, yeah, this person's progressing. It's not so bad right now. We don't need surgery, but maybe in the future. But take a look at what happened. Again, this is real data. This is real data that we took from patients. After their 74th birthday, they came in and they got this value. Now at this point, you're confused, or the doctor's confused. Oh, maybe this was a little worse by accident. They just had a bad day. So you can see here, if we use our algorithm, by combining OCT with VF, what we're essentially doing is we're smoothing out this progression and removing the variance, making it a lot easier to tell the progression much sooner. And so the bottom line here is, with our method here, what we found is that what typically takes 5 years to determine whether there's progression or not, 1 year is sufficient. Okay. So let me just finish off here. What are we doing currently? Well, I've taken all this research we've done at the University of Toronto. What I've now done is to bring it to Japan to see whether it also works on the data set obtained in Japan. So I'm working collaboratively with Kindai University in Osaka to test it over there. We've also taken our multidimensional testing to work with a hearing aid manufacturer, Wong, in Tokyo, Japan, who manufactures these hearing aids. And one of the big problems they have is you can't just give a hearing aid to a person, you have to fit it to them. What are they able to hear? What are they not able to hear? So from that perspective here, we're using that multidimensional testing. Finally, if you're interested in the publications, they are here for you to take a look. Please have a look if you're interested. So that's it. Thank you very much. And at this point, I guess we open it up for questions. Thank you.
Thank you very much, Professor. Already have a first question. So, Professor Yokota asks, what would be the biggest challenge in implementing this technology in clinical settings, for example, hospitals or clinics, with diagnostic or assisting devices? How do you overcome regulations such as medical device approval? So,
yes, well, thank you, Professor Yokota, for that wonderful question. It is always a problem to take technology and ideas to the clinic. First is really winning the trust of doctors, and that's why we're conducting these studies both in Canada, so at the largest clinic in Canada, but we also are now trying to do this in Japan as well too. But I think the broader picture here is we have a lot of regulations in well-developed countries like Japan, in Canada, etc. But I think all of us see that there's a real need for healthcare in other countries that may not be as well-to-do economically. And so oftentimes here, when we look at these machines that we develop, they are really, really expensive. So can we develop cheaper solutions? Can we develop faster solutions? I think this is a very pressing issue that's going to touch many different countries. So it doesn't exactly answer this particular question that you have, but we've been involved in developing portable visual field testing devices through VR displays. So instead of having a person in front of these large machines, we put on a VR device, put in a cell phone. The whole thing just costs, $300 US as opposed to, several hundreds of thousands of dollars.
Fantastic. Are there any other questions? Because that would bring me, and we only have a very short, there's one question. So we actually have, someone asked, you mentioned that you will be performing n-dimensional Bayesian updating, but as the dimensions increase, won't you be forced to use approximations due to the curse of dimensionality, which will result in a decrease in estimation accuracy? So the more dimensions we add, the more complex it will become.
Absolutely. Thank you for that question here. And I'm sorry I didn't have time. And that's what makes all of this so beautiful and interesting. Yes, that's one of the big problems that everyone faces with machine learning, with AI here, is once you increase more the dimension of the data here, you run into big problems. So how do you get around this? As it turns out, medical data is not as high dimensional as we think it is. So I did not come up with the 50 dimensions. These are what clinicians have typically come up with. And some people are now increasing this. They want to get 75 dimensions out of this. But if we look at the actual data that's been recorded through many years of clinical data, what you see is that it lies in a much lower subspace. Okay, so much so that I will tell you, for Toronto to work, we only need a database only of about 200 patients. Okay, so if we have a database of 200 patients, we are able, and their full visual field determined well, we are then able to run n-dimensional base updating, which is really incredible, and it speaks to the much lower dimensionality associated with it. But this is a really sharp question, and it's one that I think not many people know about, and I personally think theoretically it is fascinating. And this is the same reason why we're taking this method to other types of problems, for example, in sort of hearing aid fitting, to do that sort of same algorithm there.
Okay, thank you very much. In the interest of time, I will basically limit it now. So we have 2 more questions. So if you could get quick answers to those. So someone asked regarding glaucoma, could we first perform an OCT scan and use that information to personalize the visual field algorithm and shorten time it takes to measure the visual field? Visual field testing is a significant burden for elderly people. So a personalized algorithm. So for each gets their own algorithm.
Yeah, that's a fascinating question. And it'd be great if we could. I think one of the big issues that clinicians struggle with right now here is whether structural loss precedes functional loss or the reverse. So which one comes first? And I think even clinicians are not entirely sure. So great as that idea is, right now we don't know which is causing which one. So yeah, that would be my answer right now. But it's a great question, actually.
Okay, and then we have the final question of the day. Dr. Ajishi says, he was very intrigued by your discussion on evolving the algorithm using structural correlations of the topic nerve. Regarding the idea of incorporating these anatomical insights, did this emerge from medical domain knowledge, or was it discovered through the data analysis process? He would love to hear also experiences on your approach to integrate this in an interdisciplinary context. So,
well, thank you very much for that question. So I really think that we're just starting to look at this right now. So they've been mapped, basically what we call the retinal nerve fiber layer here and the pathway associated with it. But it's not always clean. And let me just tell you, by way of answering this question directly, when we looked at the algorithms back in the 2016, 2017, and there's also one algorithm put out by a Tokyo group in 2023, at the same time around Toronto appeared, they use rule-based methods to try to figure out the correlation between two different locations. So in that case their methods did not work as well as ours. In our case, we don't make any assumptions. We allow this all to be data-driven. So it looks at an existing database, and then it tries to figure out the rules directly from there without trying to put formally down or try to make some sort of assumption. So just finally, for the more general application of this, thank you very much for that question. I am actually very excited by this here because this method of multidimensional testing can be brought into psychometric testing, anything that requires very similar tests taken over and over and over again, like personalizing medicine to people. I think this can be used because the body is one sort of correlated organism here that knowing one thing actually gives you a lot of information about many different aspects of yourself as well too. So yeah, I look forward to a future where we consider these problems more fully.
Fantastic. So I hope all the questions that were asked were got a good answer. And with that, we now conclude today's session. So once again, thank you very much, Professor Wong. And then with that, I would invite everyone to follow up with his research and also maybe reach out to him if you have any other questions that could not fit in today's time frame. And with that, I will hand it over to the Curios team. Will let us know a little bit more about the upcoming sessions. But once again, I would invite you to thank Professor Wong for his fantastic presentation today. Thank you very much once again.
Thank you. Thank you for coming.
ワン先生、シュムハ先生、ありがとうございました。最後に事務局用にご案内させていただきます。まず、次回のブラウンバックゼミのご案内です。次回は12月24日水曜日12時10分より、九州大学男女共同参加推進室の川野金子教授より、冷たい環境とは何か、STEAM 分野に女性が増えない本当の理由と題し、講演を実施いたします。詳細はホームページをご覧ください。